here's the kind of scheme I'm going to use to represent the release of energy. This is a technique borrowed from chemistry. It's a reaction diagram. And you can see along the x-axis, it's very abstract. We have what's called the reaction parameter. But what's important to remember is that over here we have reactants, and over here we have the products of the reaction. So if I'm talking about methane, this would be some methane and some oxygen floating around. We apply a little heat so that the individual molecules can overcome the repulsion between them because they both have these clouds of electrons around them, smash together. Right? The carbon recombines with the oxygen, hydrogen recombines with the oxygen, and in the process, much more heat is released than is put in. Right? So you have an amount of energy required to accomplish the reaction, and the amount of energy released is noted here. And you can see, just for fun, I mean, through what happens if you add a catalyst. So if anyone asks you what a catalyst is, you can say it decreases the amount of energy required to obtain a chemical reaction or any other kind of reaction. You can have a catalyst for a physical reaction or a nuclear reaction without affecting the amount of energy that's released. So you don't get more energy out when you use a catalyst. It's just you don't have to use as hot or as compressed a gas or working foam in which to obtain a reaction. Right. So now we get to the kind of the backbone that I wanted to show you guys. So if anyone doesn't understand this graph when I'm done explaining it, you have to raise your hand in the ear and ask me a question. Otherwise, the rest of the talk is going to be completely lost on me, and I will have failed in my mission as a second-rate educator. I'll be third-rate. I'll be consigned to the third-rate or below even, which would be horrible. All right. So here along the x-axis, this is not a reaction diagram, by the way. This is a simple chart. We have the number of nucleons in a given nucleus. Right? And a nucleon is a proton or a neutron. It's just one of the building blocks of nuclear matter. And here we have what's called the average binding energy for nucleons. So you remember when I said when that CO2 and water are more tightly bound than methane and oxygen. So you had to release some energy in order to get those molecules to bind together, right? But you can think of this intuitively that methane and oxygen are easier to pry apart than carbon dioxide and water are. Right? It takes less energy to pry apart the methane and the oxygen. And that energy difference, because energy is conserved, when that reaction occurs, that energy has to go somewhere. So an increase in binding energy, right, the amount that you would have to pull in order to get these things to come apart, corresponds to a release of energy in the reaction. So it would make a little bit more sense if I were to flip this graph upside down, but this is the kind of graph you'll obviously see if you take an actual nuclear physics course, God forbid. So here we have the proton, which is 0 because there's nothing to bind it to, it's just one proton. Deuterium, right, which is a proton and neutron stuck together, right, and that's more tightly bound than having nothing bound. And then the binding energy more or less increases with a couple hitches, a little bit more, until you get to iron 56. And then it decreases from there. So in order to have a favorable reaction where you release energy, you have to either go from a light nucleus towards iron, ignoring those hitches, or from a heavy nucleus back towards iron. So you go from a heavy nucleus towards a lighter nucleus until you get to iron, right? Or if you're lighter than iron, you go from a light nucleus to a heavy nucleus. Right? That's why fusion works for light nuclei and fission works for heavy nuclei. You can't switch those. All right. So did everyone understand that, or somebody come tackle me? Okay, good. Right. So now we can use a reaction diagram just to quantify what I said earlier. For fusion, the amount of energy you have for bound nuclei is very low. Right? These are nuclei that are very close together. So you can think of this, nameless reaction parameters being kind of like distance. And as these things get away from each other, it doesn't matter whether they're here or here because they effectively, don't see each other. They're interacting over a nuclei at that point. So they assume some fixed energy in infinity. So for fusion, they fall into a deep well being bound. For fission, that well is like a little lump at the top. You get a lower energy when you have them separated. And always you have this barrier between here. which means you have to provide some energy in order to get some back. Right? This, in a very loose sense, is why nuclear fusion has not been the workhorse of power generation that it could be, because that barrier is very high. And to try and compress and heat a light gas and ionize it in order to obtain nuclear reactions has proven to be a massive engineering challenge. And that's an understatement. So, this being, the sole difficulty that I'll say in nuclear fusion is sweep the rest out of the way. We can move on to application. So, from Wikipedia, I've gone and taken a map of the world that has Earth's biggest producer of uranium marked in green. And all the other, podunk secondary producers of uranium are marked in yellow here. There's about 40,000 tons produced every year out of a 4 million ton reserve of uranium. I don't know if you guys can all see that, but I'll read the numbers to you. And as you can see on this map, I've marked all of the locations where there's a ready supply of deuterium in white. Those are the Earth's oceans. There's a natural abundance of deuterium in water. So if you can separate water molecules based on how heavy they are, right, which shouldn't be easy. The difference between a water molecule with a deuterium atom in it and a water molecule with a hydrogen atom in it is about 5% by terms of mass. So you should be able to weigh these things, right, with some measure of accuracy using a gas chromatograph or other kind of filter. And there are, I did this, I didn't do this on the back of an envelope to be authentic, but I did do this on a piece of scrap paper from something I printed by accident, so it's almost as good. There are 48,000 gigatons of deuterium, and that's just the gas. That's not, the oxygen you get with the water, which is worthless in terms of fusion. Yeah, oxygen he needs it just take it off and the atmosphere. So, this kind of resource, while I'm not going to say, any resource is infinite, this one will certainly be around until we leave Earth for day trips. So it's this is definitely the long-term supply of energy that will be required for the future on Earth. And that doesn't just count for Earth, but the Moon, Mars, and Venus, as we'll see later. Earth's oceans are the major supply of deuterium. All right, so where can we find the supply elsewhere in the solar system and outside the solar system? There have been a few ideas about using the protons in the interstellar medium, right? If space is not a vacuum, there's some stuff floating around there, not a lot, mostly protons. You take those protons with a big scoop on the front of your spaceship, fuse them together, and then blast the helium that you get at the back with an increased velocity, and that'll be how you move forward, kind of like a ramjet. This is, somewhat feasible. There are some technical problems, there are some physical problems with it, but it works in theory. What works even better is using Jupiter as a reserve of deuterium. Because while you have protons out here, that's all well and good. If you start your fusion with deuterium and tritium, or deuterium and a proton, it's easier from an engineering standpoint. Time to go into why, but suffice it to say that deuterium is what we want, and Jupiter contains 0.6% of the mass of the Earth in deuterium alone. So Jupiter is about 90% hydrogen and a natural abundance on the order of 10 to the minus 5 of deuterium in that hydrogen. And Jupiter, of course, is more massive than all of the other planets in the solar system combined. So we can easily conceive of a spaceship that would leave Earth, would leave the Earth deuterium economic zone, which would encompass the Earth moon orbit, Mars and Venus, and the big fuel stop on the way out of the solar system or towards the other planets would be Jupiter. You could approach the spaceship, skim the surface of the atmosphere on a slingshot orbit, and the energy you lose from drag would be more than made up by the fuel that you've assimilated.